Hi, welcome back to Calculus 4. Let me do a very quick recap from last week. Last week, the key concept that we discussed is about factors. So last week, we discussed factors. And to be specific, one important concept that we discussed is whether a set of factors are linearly independent or not. So, for example, if you have phi1, phi2, all the way up to phi(n), and then you ask yourself, are they linearly independent? Okay? And how do we do that? The way to do that is by definition. We suppose we have a bunch of scalars. Okay, we have suppose, okay, alpha 1, phi1 plus blah 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 up to alpha n, phi(n) is the CO factor. Then when you're comparing the coordinates, you obtain a system of equation. A system of equations. Then what you try to solve is that, okay, of course, you try to solve the system equation. If you discover that at the end, all the scalar, so alpha 1, alpha 2, up to alpha n, it turns out to be 0. So it turns out if this is the only solution to this equation, then we say that this set of factors is linearly independent. Okay? So in the process of investigating whether a set of factors is linearly independent or not, you have to resolve a system equation. And then this week, we're going to discuss matrices. Why do we study matrices? Because matrices is an effective way to organize a system of equation. And we are hoping that by introducing the concept of matrices into our story, we can understand factors in a more efficient way, okay? So that's why this week we focus on matrices. So I guess many of you have already seen matrices when you were younger, but nevertheless, I'm going to start from scratch. In particular, I need to tell you the basic terminology regarding matrices. So what is a matrix? A matrix basically is a table of numbers, okay? It's a table of numbers. So two important terminology are what it means by rows and columns of a matrix. So what are rows? Rows means the horizontal array, okay? Horizontal array. So this is called the first row. So first row. And of course, this is called the second row, and so on. So rows are given by horizontal array, okay? How about columns? Then columns are the vertical array. So this is the first column, second column, third column, and so on. So these are called columns. So this is the first column, and then and so on, okay? So columns means the vertical array. And then, okay, so let me put box here to remind you. So it's very important that next time when I say columns and rows, you know what I'm referring to. So rows are the horizontal array, and then columns are the vertical array. And then moreover, in this case, we call A M by M matrix, okay? Why? Because M is the number of rows of A, right? If you count it carefully, 1, 2, all the way until M, so you have M rows. Okay, M rows. So let's separate them. And then, what is N? N is the number of columns. Of A. For example, in this case, well, there are n columns. You got 1, 2, 3, all the way up to n. So n columns. So when a matrix have m rows and n columns, we call it a m by n matrix. Okay, so this is important. Don't mess up the order of m and n. Okay, be careful about this. So so there are two basic examples of matrices that actually we have discussed, we have seen last time, because factors is really a kind of matrix. For example, a column factor can be really regarded as a m by 1 matrix, okay, m by 1. Whereas a row factor, a1 to an, can really be regarded as a 1 by n matrix. Okay, so in this way we can regard factors as a special kind of matrices. So one important operation between matrices is that you can multiply them. So I guess many of you have seen multiplication matrices before, but I'm going to recall what it is for you anyway. It's very important to note that not any pair of matrices can multiply together. The only case you can multiply matrices together is when A is a m by n matrix and B is a m by p matrix. Okay, let me make it more precise. So we have A, B. So when can we multiply them together? Is when A is m by n. So m by n means you have n rows and n columns. And then B is m by p. So you have n rows and p columns. Only when the number of columns of A and the number of rows of B agree, you can multiply them together. But then the resulting matrix, okay, the resulting matrix turns out to be a m by p matrix. Okay. Let us get it more precise how to do this multiplication. So A is an m by n matrix. In particular, it has n rows. Okay, n rows. Row means horizontal. So let me call the rows phi1, phi2, all the way up to 3m. And then B has p columns. I'm going to call the columns W1, W2, up to WP, WP, so P columns. And then it turns out the resulting matrix would be a M by P matrix. So if I call the entry C11, C12, up to C1P, and then C21, C22, up to C2P, and I know I have M rows, so I have CM1, CM2, up to CMP. Okay? Then you ask yourself, how do I get the, well, IJ entry? Okay, IJ entry for the A1, C, the 11 entry. How do I get that? So, how do I get that? Well, the Cij entry is really just the inner product of, okay, of what? Of the ith row of A and the jth column of B. So how do I get, in general, a Cij entry in the middle? That is by taking the inner product of the ith row and the jth column. So while using a notation we learned last time, this is given by Phi, comma Wj. So for example, how do I get C11? So C11, I should take the first row and then dot product with the first column of B. Okay, so would be first row of A, comma, so dot product or inner product with the first column of B. And then how about let's take a random entry, for example, A2P. Okay, A2P. Sorry, C2P. How do I get to see the 2p entry of the product? That is by taking the second row and the pth column and take the inner product together. So V2 and WP and etc. Okay. So this is how we defined a multiplication of two matrices. Of course, if we write in such a way, it's a very messy way, so it's a lot easier when we get to some concrete example, and that is what we're going to do on the next page. Okay, let's look at some example. So they asked you to perform, if possible, the following multiplication of matrices. The first one, I have two matrices. The first one is a 2 by 2 matrix. The second one is a 2 by 3 matrix. Then we know that in this case, it's possible to perform the multiplication because these two numbers agree. And then the resulting matrix would be a matrix of the form 2 by 3. Okay, 2 by 3. So it's a 2 by 3 matrix, the outcome. Okay, let's get it concrete. How do we multiply matrices together? So I have 6 entry, right? 6 entry, 1, 2, 3, 4, 5, 6. So how do I get the first entry? The first entry here is the 1, 1 entry. Or in other words, I need to take the dot product between the first row of the first matrix and the first column of the second matrix. So if I take the dot product of these two, then I get 4 plus 6. Okay, right? If I take the dot product of these two, I get 4 plus 6. How about the next entry? The next entry is the 1, 2 entry. So to do this, we're going to take the first row and the second column and take the dot product. So the dot product will be -1 plus 8. And so on. So the third entry here will be the dot product of these two. So 2 plus 0. How about this one? This is the so-called 2, 1 entry. 2, 1 entry, that means that we take the second row and the first column to take that dot product. And then in this case, it will be 12 plus 12. And going on, this is the so-called 2, 2 entry. So you take the second row of the first matrix, the second column of the second matrix, then take that dot product. So you get -3 plus 16. And finally, is the 2, 3 entry. So second row of the first matrix, third column of the second matrix. So the dot product is 6 plus 0. So after you compute them, you get 10, 7, 2, 24, 13, 6. Okay, so we're done for the first multiplication. So let's do another example. So two very similar looking example. The first one is CO1, CO0 times CO010. So both of them are 2 by 2 matrices, and in particular, these two numbers agree, so we can multiply them. And then the resulting matrix is also a 2 by 2 matrix. Okay, a 2 by 2 matrix. So how can I obtain the entries? This one, the 1, 1 entry, is obtained by taking the first row of the first matrix, the first column of the second matrix, and take the dot product. And then in this case, the dot product, if you do it quickly, will be 1. Okay? And then moving on, the first row, second column, the dot product is 0. And then this is 2, 1 entry, so you need to do the second row, first column, so it's also 0. And finally, 0, 0, so 0. How about the other one? The other one, okay, let me call this the first one. First one. The second one, it's very similar. Basically, you swap them, okay? You swap them. And then we perform the identical operation. So the first entry, A11 entry, will be given by the first row, first column, dot product 0. First row, second column, dot product 0. Second row, first column, also 0. And finally, second row, second column, 1. But something interesting happened. Okay, something interesting that is different from multiplication of real numbers is that the order of multiplication is very important. It turns out, well, for example, you call it A and B, A times B and B times A can be different. Okay, because these two matrices are obviously different. So let me put a warning here. So remark. In general, if you have two matrices, A times B is not B times A. Okay, so this is very different from numbers. Numbers, it does not matter which order of multiplication you take, but for matrices, the order of multiplication is very important. So let me put a box here. Okay, so let us do the last example. The last example, you have the first one, that is you have 1, 2, 3, 4, 5, 6, and at times a column factor x, y, z. So what is this? This is a 2 by 3 matrix, and this is a 3 by 1 matrix. So in this case, we can multiply them because these two numbers agree, and then the resulting outcome would be a 2 by 1 matrix. Okay, a 2 by 1 matrix. So how do I multiply them? 2 by 1, that means that it's of this form. So this is the 1, 1 entry. So we're going to take the first row, first column, and then take the dot product. So I get x plus 2y plus 3z. And this entry is the 2, 1 entry. So I'm going to take the second row, first column. So 4x plus 5y plus 6z. Okay, so this is how you perform multiplication in this case. How about the second one? The second one is 1, 2, 3, 4, 5, 6. But then instead of a column factor, and then we have row factor. But there's an issue here because this one is a 2 by 3 matrix. However, this one is a 1 by 3 matrix. These two numbers do not agree. Therefore, this multiplication does not make sense. Okay? Why do I need to mention this example? Because last week, someone asked me why someone would bother to write factors in a column form. It's because column factors is good for doing multiplication. Okay? So let me do a remark. So from this, we see that column factors are good for multiplying with matrices. That's why the notation of column factors is also widely used in many contexts, especially in the context of linear algebra, because they can multiply with matrices naturally. Okay, so let me put a box here. So I hope that the example on this page will get you familiarized with how to perform multiplication of matrices.